Let us have a look at the average output voltage. The average output voltage in the case of R load and L filter with R load is given by this integral. VO average is equal to 1 by pi by 3. Now the repetition is just pi by 3, so I am talking about the average of this purple color waveform. So we can integrate this waveform from pi by 6 to pi by 2, because the value is equal to VRY, and you will have another similar wave shape but of another line to line voltage in the next 60 degrees. So it is enough if you integrate for 60 degrees. That is what is done here. So 1 by pi by 3 integral pi by 6 to pi by 2 VRY. If you do this integral, the average output voltage will turn out to be 3 root 3 Vm by pi, and the average output voltage will be same in both cases, R load and L filter R load. The maximum value of output voltage is peak line to line voltage, which is root 3 Vm, and the peak to peak ripple in output voltage is root 3 Vm minus 1.5 Vm. So as you see, it is much better than 3-pulse rectifier and 2-pulse rectifier. In 2-pulse rectifier we were going down all the way to 0, and in 3-pulse rectifier we were going to half Vm, and now the peak value is 1.5 Vm. And the frequency of output voltage ripple is 300 Hz, which is 6 times the line frequency. And each diode conducts for 120 degrees, 1/3 of a line cycle, whereas 2 diodes conduct together at any given point of time. Let us try to compare the waveforms of input current drawn with different kinds of loads in the case of a diode bridge rectifier, 3-phase diode bridge rectifier. We have already seen this waveform with R load, and the peak value of the waveform is denoted by I peak, and it is equal to root 3 times Vm divided by R, because root 3 Vm is the peak voltage that is appearing across the output. When you bring in a C filter, we will be drawing currents from source for very short intervals, and in those short intervals there will be a peak current I peak, and the value of I peak can be calculated as this root 3 times Vm by R sine delta dash plus omega c Vm cos delta dash, where delta dash is pi by 3 plus delta. This expression can be derived in a similar manner that is followed for half wave rectifier and full wave rectifiers, single phase half wave rectifier and single phase full wave rectifiers. And when we have an L filter with R load, the current is going to have a sinusoidal plus exponential waveform for 120 degrees, and then it's going to be 0, because no diode can conduct in one phase group for these intervals, and the same is going to repeat in the negative half. So the waveform is going to be symmetric. The average value of this particular sinusoidal plus exponential part, that is denoted by IP here, and that is equal to 3 root 3 Vm by pi times R. And when you increase the value of L, the peak to peak ripple, this ripple becomes smaller and smaller, and the source current becomes a quasi square wave like this. One interesting point here is that in all these 4 waveforms there are no even harmonics, because there is half wave symmetry, and by Fourier series, the Fourier analysis, it can also be shown that there will not be any triplen harmonics. That means harmonics of the order of 3n. So the order of harmonics present in source current waveform in all these cases is 5, 7, 11, 13 and so on, which can be written in general as 6m plus or minus 1, where m is equal to 1, 2, 3 and so on. Now looking at the special case of R load with a large L filter, where the output current will almost be a constant, and which is represented by IO here. So in that case, the shape of source current will be a quasi square wave as discussed earlier. Let us try to analyze this waveform and look at its THD and power factor and so on. So the fundamental component of IR, IR1, is also shown here in dotted lines. Then the total RMS value of this IR, the solid orange color waveform, is IO times square root of 2 by 3, and the RMS value of the fundamental component, which can be obtained through Fourier analysis, will turn out to be root 6 by pi into IO, and any nth harmonic magnitude is simply IR1 RMS divided by n. This can also be proved mathematically by evaluating the Fourier series. And how about the displacement power factor? When we say quality of current waveform, we are interested in the wave shape and also the phase difference of the fundamental component with respect to the source voltage. Here we have considered one source voltage and one source current. The same can be done for all the other remaining sources, VYN, VBN and so on. So the angle between VRN and IR1 is 0. The phase angle is 0. That means the displacement power factor is unity. But as seen from the waveform, it is clear that there are unwanted components in this waveform, so there will be a distortion factor, and the distortion factor can be shown to be 0.955. That makes the total power factor as 0.955. And the order of the harmonics we have already discussed earlier, and the total harmonic distortion in the input current waveform will turn out to be 31.08%. Please note that this THD value is less than that of a pure square wave. The pure square wave has 48% THD approximately. This quasi square wave has about 31% THD. Now coming to the output voltage waveform, because in a rectifier we are always concerned about output voltage or input current and input current. So the output voltage waveform in the case of R load will be a periodic waveform at 300 Hz. The maximum value of the waveform is root 3 Vm, while the minimum value is 1.5 Vm. The average value is 3 root 3 Vm by pi, as we have seen. If you put an L filter, that will smoothen out the current, which will in turn smoothen out the voltage that is getting applied across R. However, the average value of the output voltage will remain the same. Why? Because when you have R and L, and if you are looking at the voltage VO and VO dash, both have the same average value, because the average value of the voltage across inductor is 0 in periodic steady state. So VO dash average should be equal to V average, and as long as this current is continuous, VO dash average is going to be same as this, and that is what is shown in this green dotted color waveform. But the waveform of voltage across R, which is the output voltage, is also shown in purple color here. So the average value will be 3 root 3 Vm by pi. When you increase the value of L, for a large value of L, we get the average output voltage to be almost 3 root 3 Vm by pi. When we have a capacitive filter with R load, the output voltage will again be a periodic function at 300 Hz, but it will be either sinusoidal or an exponential fall. The sinusoidal portion of this waveform will be one of the line to line voltage waveforms. The sinusoidal voltage appears at the output whenever diodes are conducting. That can be seen from this zoomed figure. So the output voltage will be sinusoidal, for example from pi by 6 plus delta to pi by 3 plus gamma, and that will be equal to VRY, and it will fall exponentially, and after pi by 3, after 60 degrees from this pi by 6 plus delta, we will have another sinusoidal variation starting, and then that will again stop here and it will go on. The average value of output voltage for this case is given by this expression, which is a function of gamma and delta dash of course for a given Vm, and delta dash is pi by 3 plus delta, and again tan gamma is 1 by omega RC. Delta can be solved by following the method described earlier. So to summarize module 2, in this module we have learnt the characteristics of a diode. We looked at the construction of a diode, and we looked at its VI characteristics, and we also looked at its transitions, state transitions, and we calculated the power loss. We learnt how to calculate the power loss in a diode. Then we also have learned the method of assumed states to determine the state of a diode, whether it is on or off, in different circuit configurations. And we looked at 1 pulse, 2 pulse, 3 pulse and 6 pulse diode rectifiers. These are essentially AC to DC power electronic converters. And we also have looked at different configurations of load, a pure resistive load R load, or we have L filter with R load which smoothens the output current. And we also have considered the case of a very large inductance being present, which is almost a constant current load. Then we also have looked at C filter with R load. Having a capacitive filter smoothens the output voltage, and we have also learnt about RLE type of load which represents a DC motor.